Hey everyone, so on Friday here we left off just talking about how traits may be inherited, how different types of traits may be inherited, and some traits are what we call single gene traits, so with one gene, one phenotype. And we might see in a population that those phenotypes may be displayed on a graph as such, right? So take, for example, widow's peak in us humans. So a widow's peak is that classic sort of Dracula-like appearance to your hairline, right? And widow's peak is, I'm under the impression widow's peak is dominant to straight hair, so where you might just have a straight hairline. But either way, it doesn't matter. It's one gene produces either this widow peak appearance um, or the other allele gives you no widow's peak. So you have this either or, right, in a population. When you look at polygenic traits, so these are where several genes are determining your phenotype. And so some examples in humans could be things like height. So if you look at our population, we're not all just really tiny or really big, right? In which case, we'd be at this end or at this end, but we're everything in between. And when you look at this distribution, we don't see an either or, right? So this kind of gives this either or scenario, right? Things like height, skin color, there's many different traits in our genetic makeup that are controlled by several genes. And what we tend to see is a spectrum with respect to the phenotype, right? So remember, these graphs are showing the phenotype, the distribution. So if we look at height, yeah, maybe there are some individuals in the population. Again, here's our frequency, right? Frequency of the population that are really short, and maybe a small frequency that are really tall, but there's everything in between. So why do we consider this in terms of talking about evolution? Well, let's go back up to here for just a second and think of if natural selection acts on favorable traits. Imagine if we take a single gene trait like widow's peak, and I don't really have a interesting analysis in terms of how nature could act on our hairline, but let's assume that widow's peak gives individuals an advantage. Maybe it's just that much more attractive to females than the straight hairline. I should not be talking about this given the bald guy, but anyhow, let's assume that that's the case. And so women may select this, and over time, we might see an increase in widow's peak and maybe a decrease in no widow's peak, or maybe none at all over time. But when we look at natural selection on polygenic traits, we actually continue to see the diversity. If you think about this is greater diversity than this scenario where you just have two situations. This has a whole blend of situations, right? So let's look at what happens when natural selection acts on these polygenic traits. So polygenic traits can lead to sort of three different evolutionary changes in the population, depending on how natural selection affects the trait. So let's look at the first one. The first one is what we call directional selection. So directional selection occurs when individuals at either end of the extreme, at either end of the spectrum, are selected for. Okay, so we can imagine the dotted line. Okay, so in all of these examples, the dotted line represents the initial population, and the solid line represents the change in the population. So let's imagine this dotted line here, and if individuals at the extreme, so again, we're in this dotted line, try to envision that solid line not there, but if individuals at the extreme end were selected for, what we would see is a shift in the population for individuals more in that area. We could use an example of, let's say, beak size on birds. Okay. Let's imagine that the environment changed in such a way. So birds feed on seeds and maybe nuts and things like that, right? And so perhaps the environment changed in such a way that many plants producing smaller seeds were wiped out, and only plants producing large, maybe nuts and much harder encased shells in which birds had to try and get at the seeds. So in this case, larger size beaks would be an advantage. All right, so some change, right? Change in the environment, right, caused larger beaks to be favored, and therefore the population would shift, in which case more birds would have larger beak size or would be selected for it. Not because birds said, I need a harder or a larger beak to get into these harder shells, but simply that the variation creates, the changes create variation, and that variation is selected for based on those most fit for the environment. So we call this directional because the original population is shifting one way, or it could equally happen where maybe small beak size was more favorable, maybe larger shells and seeds were wiped out and only small seeds available, and if you had a large beak, it made it difficult to obtain food, right? So it could shift either way, but you get a direction one way or the other, directional selection. Another form in which evolutionary changes can result, or how polygenic traits can be affected by evolutionary changes in a population, is what's called stabilizing selection. So if we look at the graph down here, in this case, so when natural selection acts on the non-extreme trait value, in other words, selects for the more average form. A great example of this would be over time how, let's say, birth weights of children, right? Birth weights of children probably have a very narrow range. If we look historically, maybe, I don't know, over thousands of years or tens of thousands of years, we might have seen a more broader distribution, but babies born at extremes might have a lower chance of survival. I mean, we can see that with preemie babies now, right? The only advantage being is our technology to support those preemies through a few months until their size increases and their survival rate increases. But if we go back before technology and the advent of medicine and neonatal intensive care units, nature itself would have selected for a more stabilizing norm in birth weight, right? Why we see averages centering around 7 pounds more likely than, say, at the extremes of 3 to 4 pounds, or say, 10 to 12 pounds. The last one is what we refer to as disruptive selection. I don't have much space here down at the bottom, but here in disruptive selection, individuals at the extremes of a particular phenotype are selected. Right? Individuals at the extremes of a particular phenotype are selected, and so Here's our, if I draw in red, or sorry, in blue here, here's our original population, a normal distribution for a particular phenotype, right? But for whatever reason, individuals are at the extremes, so at this end, are selected for, and therefore we would see an increase in the population at the far end, at the near end here, and a dip in the middle to exaggerate it a bit more, and an increase in the appearance of individuals at the other extreme end. So we get kind of this disruptive selection. So important to consider, right? If we go back, Darwin didn't know about all this information about our DNA and genes and alleles and such, and the idea of single gene traits versus polygenic. So, but these are all things that can influence evolution in different ways, right? When we look at the evolution of polygenic traits, we see a variety of different effects of natural selection, either directional selection, stabilizing selection, or disruptive. You want to make sure you understand those and understand how these graphs work. That's first video, so stay tuned for video number 2.